guys, welcome to your very last AP chemistry lecture. How crazy is that? I can't believe we made it. But just like the last one, disclaimer, it might sound like some things are out of order because I might say first we're talking about or whatever, because I flip-flopped the order from last year. But anywho, in this lesson, you're going to be talking about types of solids and their structure, how liquids behave, especially then the bulk of this is going to be about intermolecular forces. So how are actual molecules attracted to other molecules?
We're going to start by talking about solids. So in general, solids have definite shape, definite volume. So regardless of their container, they're not going to take the shape, they're not going to change their volume. They have our least amount of kinetic energy, meaning our particles are moving very, very slowly. So their motion is limited and their particles can't move or slip past one another. So very much fixed in place, but don't think of it as they're not moving at all, because the only way particles would ever stop moving would be if we were at absolute zero. But they're moving very, very, very slowly. So solids can be either crystalline or amorphous. So crystalline solids are when atoms or ions or molecules, whatever's making up the solid, is in a definite repeating pattern. So very ordered. We have four major types of crystalline solids that we're going to go through in just a second. Amorphous solids, so just as the word indicates, are without shape. So that's when the atoms, ions, or molecules are totally random. This is much less common, and it occurs when a liquid phase of the substance solidifies or freezes before its molecules have a chance to become arranged. So typically molecules are going to arrange themselves nice and neat before full solidification happens. But if that doesn't happen, we have an amorphous solid. And so some examples of that are glass. That explains why glass shatters in so many different directions and never the same way. Candle wax is another example of an amorphous solid. So now we're going to go through our four crystalline solids. The first are ionic solids. We should be very familiar with these. Those are just our ionic compounds. So we've got positive and negative ions being held together by their electrostatic attractions, so that they're opposite charges. Super high melting points, hard and brittle. They don't bend, they shatter. Can't conduct electricity as a solid, but they do if they are aqueous or in their molten state. Metallic solids, we've also talked about these. So they're formed by metal atoms in a uniform distribution of their nuclei with a sea of delocalized electrons. We talked about this last unit. We do call them held together by metallic bonds. They have really good electrical and thermal conductivity because we have those kind of free valence electrons that can move and pass along a current. They're super lustrous, malleable, and they have a very wide range of melting points, but they're going to be high compared to like our molecular compounds. Alloys are a type of metal solid. They're a mixture of metals, but they're going to have the same properties as our metallic solids we saw on our last slide. So there are two types of alloys. There is one called substitutional, which is where your host metal is replaced by atoms in similar size. So an example of that is brass, because brass is a combination of copper and zinc. And if we look at copper and zinc on the periodic table, they're very close in size. And so you can see in the picture at the bottom on the left where we took our host metal, our pure metal right here, and we replaced some of them with atoms that are very similar size. Another type of alloy is interstitial. And so you can think of substitutional as literally swapping out, interstitial like putting them in between. So this is when smaller atoms are kind of shoved in there to take up the empty space. So that's this example right here. An example of that is steel. Steel is a combination of iron and copper. And then finally, you could have a combination of both, where we have some substitutional and we have some interstitial. One thing to note is that an interstitial alloy will make the solid more rigid because you've taken up a lot of that empty space. It's going to become less malleable and ductile than just the pure metal would be. A covalent network solid are really interesting solids. They're not super common. They're when atoms are held together in a 3D network by actual covalent bonds. In one example, it is a sheet of 2D covalently bonded, and that example is graphite. So only non-metals are going to make up, excuse me, only non-metals are going to make up covalent network solids. So you're never going to see a metal here. Some examples are diamond. So something that's really interesting to point out is obviously diamond and graphite are both made out of carbon. They're both covalent network solids. The difference is that diamond is in a 3D network. So all these carbon atoms are covalently bonded in these large structures that make it extremely hard and strong. Graphite, however, is in a 2D network and they are in individual sheets. So graphite is a weird exception to the normal characteristics of network covalent solids because those sheets can slide easily past one another. And so that's why we use it in our pencils because it writes on paper. Silicon dioxide sand is another example of covalent network. They are going to have extremely high melting points because you have to overcome covalent bonds in order to melt or boil them. So we'll see that a little bit more later this unit when we talk more about intermolecular forces and how that relates to boiling point. And finally, we have molecular solids. So these are just neutral covalently bonded molecules. So the examples down here are like iodine. So it's a diatomic. And so if it is in its solid state, or like carbon dioxide, if we were able to solidify that. The strength of the attracted forces totally just depends on the individual molecules themselves, but they're typically going to have lower melting points when compared to our other types of solids. The example I give you here, carbon dioxide, its melting point is negative 78 degrees. Like that's why we don't see carbon dioxide as a solid. Whereas iodine, its melting point is 114 degrees Celsius. So it is more common to see it as a solid. If you did look at the POGL, this is the chart that was at the beginning for you to kind of compare the different types of crystalline solids, the four that we just went through. And this chart combines all of their properties all together. So this would just be a good thing to use to study. So it talks about what particles make it up, what kind of attractions there are between the particles, what their properties are, and gives you some good examples. So now we're going to move on to liquids. We don't have lots of examples of types of liquids like we did with our solids, but we're going to go over some just general properties. So liquids have a definite volume, but they don't have a definite shape. So what that means is I could take a liquid of 5 liters and I can pour it into a bigger container and it's going to take up the shape of that larger container. It's not going to change its volume. It's still going to be 5 liters, but it could take the shape of that new container. They have that medium amount of kinetic energy, so they do have enough energy where they can move and collide and actually move past one another, but not enough energy to actually escape like a gas would. So some unique properties of liquids. Liquids have a viscosity, which is how resistant it is to flowing. So you can look at the examples below: water, olive oil, honey. Honey is obviously going to have that super high viscosity where water has a very low viscosity. Liquids show cohesive forces, which is when their intermolecular force of attraction between the same molecules, so like 2 water molecules being attracted to each other, this is what causes liquids to form drops. So if you're looking at like rain rolling down a windshield, like it forms droplets because of the cohesive forces between the water molecules. But they also show adhesive forces, which is where the intermolecular forces of attraction occur between 2 separate molecules. So like water being attracted to the glass of the windshield. Liquids show high surface tension. So surface tension is the energy required to increase that surface area. So because water has super high surface tension, that's why you can see these little bugs that can like hop along the water without breaking down into it. That's how, if you've ever done, like you float a paper clip on the top of water. And then capillary action is when the adhesion of the water molecules or whatever liquid to the surface is higher than the cohesive forces, and so it allows it to kind of move up against gravity. So a paper towel soaking things up is an example. Roots down in the soil, and then the water is able to move up against gravity up the tree. If you've ever done the cool little paper towel experiment where the one here shows the yellow water and the blue water, and then it moves up the paper towel and it'll eventually combine in the middle cup to make green water. All right, one of our final topics for this unit, intermolecular forces. So intermolecular forces are various attractions that exist between atoms and molecules of a substance. They're also called van der Waals forces. So kinetic energy is required to overcome these forces. So something to get straight in your head right now is that a bond, such as a covalent bond, is not an intramolecular force. It is an intermolecular force. So this example is showing us that we have hydrochloric acid or hydrogen chloride. This covalent bond is an intramolecular force because intra means within. But this intermolecular force, the attraction between the two molecules, between. Intermolecular forces are always going to be weaker than intramolecular forces. Right now we're focusing on intermolecular forces. Our first kind of broadest type of intermolecular forces are dispersion forces, also known as London dispersion forces. So dispersion forces are for non-polar molecules. So dispersion forces are the, let me rephrase that. Dispersion forces are the only intermolecular force experienced by non-polar molecules. So how can a nonpolar molecule be attracted to another nonpolar molecule? This results from something called an instantaneous dipole or an induced dipole. What that means is you've got your electrons kind of zooming all around, evenly distributed, but there could instantaneously be a time where they're uneven. Or if a nonpolar molecule is nearby a polar molecule, that polar molecule can pull on it and temporarily induce a distribution that's not symmetrical. So dispersion forces are our weakest intermolecular force. They're very much affected by the size and the shape of a molecule. And then again, I want to reiterate that all molecules have dispersion forces, even if they have other intermolecular forces. So I want to revisit this idea of the size and shape affecting the dispersion forces. So larger or heavier molecules are going to have greater dispersion forces due to something called polarizability. And the polarizability is just a measure of how easy or difficult it is to distort that molecule's charge. So what we mean again by that is like if this, sorry, my pen died. It's the worst. So if this molecule is evenly distributed right now, the electrons zooming around, at some point it's possible for them to get slightly kind of distorted. And in that point, it would have a dipole. The larger something is, the easier it is to distort it because it has larger electron clouds and they're further away from the nucleus. And we see that if we look at our halogens. So the melting point of fluorine is 53, which has a molar mass of 38, where for iodine it's 387 Kelvin, 254 molar mass. So as we increase in our size and our weight, we increase in our intermolecular force. We see that because the melting points and the boiling points are going up. The next type is dipole forces. So dipole forces have to involve at least one polar molecule that has a dipole moment. So if you remember from last unit, we talked about polar and nonpolar molecules. And we talked about how even if we have polar bonds, such as the carbon-oxygen double bond and carbon dioxide, if they are symmetrical, the whole molecule is non-polar. So this does not have a dipole moment. While this over here, like water, is polar because our polar bonds are not symmetrical. They don't cancel each other out. So that gives the entire molecule this large dipole moment. So we have three different kinds of dipole interactions. We can have ion dipole. So an example of this would be like water and salt. So that's the attraction between the charged ion and a neutral polar molecule. So if we have a polar molecule and it's going to be attracted to an ion, this is actually our strongest dipole force. So here's an example. So this would be like chlorine and sodium attracted to water molecules. Our next dipole forces. So that is in between two polar molecules. This kind of has the middle strength of our dipole interactions. So if we had like two hydrogen chloride molecules, the attraction between them is going to be dipole, or like two water molecules. Any two not polar, any two polar molecules are going to have dipole forces, as the name suggests. And then our final one is dipole-induced dipole. So again, in order to have a dipole force, you have to have at least one polar molecule. But what we mentioned before with the dispersion forces, a polar molecule can induce a temporary dipole moment for a non-polar molecule. So let's look at this example down here. Oxygen gas, O2, is absolutely nonpolar. It is symmetrical distribution of its electrons, and so it is nonpolar. But let's say we put it with a water molecule who is absolutely polar. What can happen is this water molecule can temporarily distort the oxygen, giving it a temporary slight charge and a slight dipole moment, and that's going to create this interaction that's being shown in the picture. That's our weakest type of dipole-dipole intermolecular force because it's only an induced temporary dipole. Our last intermolecular force is hydrogen bonding. This is the one you're probably the most familiar with. Despite its name, I want to point this out right now, it is not a bond. It is not a covalent bond. It doesn't happen within a covalent molecule. It's between certain molecules. So hydrogen bonding really is a special type of dipole-dipole bonding, and it's the strongest type because it's when hydrogen is bound to a fluorine, oxygen, or nitrogen. So most of you remember that as not. Okay? So the graph down here is showing our boiling points. And we're going to talk about this in a minute, but remember, higher intermolecular forces means higher boiling point. So what this graph is showing is it's showing different groups bound with hydrogen, group 17, 16, and 15. And we're not including the first option, which is going to be oxygen or nitrogen, oxygen, and fluorine yet. But then the rest of the period, we notice we increase in boiling point. So that means we're increasing in intermolecular force. So this one has the weakest. So we would expect this one to be lower. But when we actually look at it, it's absolutely not. It is exceptionally higher. And the explanation for that is the fact that nitrogen, fluorine, and oxygen are so electronegative that that causes the intermolecular forces between these molecules to be hydrogen bonding, which allows them to be extremely attracted to one another, and it takes a lot more energy to break them down. So hydrogen bonding is our strongest intermolecular force. Just because hydrogen is there does not make it hydrogen bonding. So for example, if we have hydrogen connected to a carbon, and there is an oxygen within the molecule, that does not mean it necessarily has hydrogen bonding. This does not have hydrogen bonding because the hydrogens are connected to the carbons, not the oxygen. Okay? So those are all of our intermolecular forces. Dispersion forces, dipole, dispersion forces, dipole forces with our three kinds, and then hydrogen bonding. The very last thing for this is kind of talking about how this relates to phase changes, because we really need to understand how these intermolecular forces and how the attraction between particles affects their characteristics. So depending on what the molecule or the substance is going to depend on what force has to be overcome to change its phase. So we're talking about an ionic bond. We have to actually overcome, an ionic compound. We have to actually overcome ionic bonds. For molecular compounds, we're just looking at intermolecular forces. And for covalent networks, that's why we talk about they have such high melting and boiling points, because we're actually overcoming and breaking covalent bonds. But something, even though in this special case scenario where we're breaking covalent bonds, still remember a phase change is a physical change. So when something changes phase, it does not actually change its chemical identity. It's just overcoming the forces that are holding multiple molecules of that substance together. So these should be familiar to everyone. Vaporization is when liquid is turning into a gas. Condensation is when gas is turning into a liquid. These are equal and opposite of one another. Something to note is vapor pressure. So vapor pressure is the pressure exerted by vapor in equilibrium with a liquid in a closed container. So we want to look at for a second at how intermolecular forces are going to affect vapor pressure. So stronger intermolecular forces are going to impede vaporization and favor condensation. So if I have really strong intermolecular forces, I'm going to have, so strong intermolecular force equals lower vapor pressure, because molecules don't want to vaporize. So remember, vapor pressure comes from gas, the gas that would be above a liquid in a closed container. So if I have strong intermolecular forces, these particles don't want to vaporize. Weaker intermolecular forces have a little bit less of an impact, obviously, so those are going to have higher vapor pressures. So something that can be a little bit confusing is thinking about this in both directions. So if I have a substance and I am increasing in my temperature, so I would be going from liquid to gas, my increased intermolecular forces is going to make it harder to vaporize. But think about if we're going the other direction. If I am starting as a gas and I am decreasing in temperature, so I'm turning into a liquid, that's going to be easier. When I have strong intermolecular forces, it's going to be easier to condense because the molecules are super attracted to each other. So when they get into close contact, they want to remain that way. So harder to vaporize, easier to condensate. Boiling point is the temperature at which equilibrium vapor pressure equals the pressure by the liquid, and so it starts to boil. If you've got an open container, that pressure is always going to be atmospheric pressure. So another relationship is intermolecular force to boiling point. The stronger intermolecular forces mean a higher boiling point. That makes sense. We just said stronger intermolecular forces means lower vapor pressure. If we've got to get vapor pressure equal to atmospheric pressure, then it's going to take longer to do that and more energy to do that. So stronger intermolecular forces are also going to mean higher boiling point. So we need to make sure that we know those relationships. Melting, of course, is a solid transitioning to a liquid, and freezing is just the opposite, a liquid changing to a solid. Our two that kind of skip a phase, we've got sublimation, so a solid straight to a gas, and then deposition, a gas straight to a solid. So an example of that is frost. So the water vapor in the air turns immediately into solid ice. Finally, our heating cooling curve, something I just wanted to point out really quickly. Remember that temperature does not change during a phase change. All of the added energy is going into breaking down those intermolecular forces or whatever it is holding our particles together and changing their phase. So I really just want to reiterate our big takeaway with intermolecular forces and phase changes is that high or strong intermolecular force equals lower vapor pressure, which gives us a higher boiling point. All right, so that's a big memorization. So if you were given a question where you were asked to compare the intermolecular forces for, let's say, compound A and compound B, and you were told that the boiling point for compound A was 120 degrees, but for B it was 500, I just wrote 400 degrees, then you would say that this B has stronger intermolecular forces. And it may ask you to identify what the intermolecular forces are. So I hope you guys have enjoyed our very last new content. If you're still with me, I'm super excited that we have finally delivered all of the information that your little brains need, and we'll officially review after spring break.